Alright, so we're going to look at, in this section, set operations. That is, how do sets interact and how do they relate to one another and themselves? So the idea is, again, to look at relationships between sets. How do sets interact? How are they going to overlap? If I put both together, what's going to happen? Those kinds of things. And there's a lot of different ways how the set can react with its universe, how the set can react with another set, and so on and so forth. So the first operation is going to be the complement. Now, the complement is essentially well, let me say it this way. We'll start with the official idea. The complement of a set is all the elements in the universe that are not in the set itself. So for instance, if my universe is the numbers 1 through 8, and I have the set A, which is 1, 2, and 3, then the complement of A, which we're going to denote as A with a slash, sometimes I'll call that A prime, is everything in the universe that's not in A. Alright, so the complement is going to include 4, 5, 6, 7, and 8. And you can see here, if I look at A and its complement, if I throw them together, you're going to get the whole universe. So A and its complement, the complement of A is everything that's not in A, everything in the universe that's not in A. Alright, so I did it very similar to A prime on the last slide, assuming this A and A prime on the last slide, but let me do another one. Here, instead of our universe being 1 through 8, we did 1 through 10, so it's going to work almost exactly the same way. We see 4, 5, 6, 7, 8, 9, and 10. And I want you to figure out for yourself what's B prime. So push pause. So you only take, again, a few seconds, and write down B prime. Alright, so the complement of B, we have 2, 4, 6, 8, 10. Basically, we have the even numbers. And so 1 is in our universe, 3 is in our universe, 5, 7, 9, and everything else is in A. So the numbers 1, 3, 5, 7, and 9 are in the complement of B. I said A earlier, but I meant B. So B has the evens, the complement has the odds. All right? So anything that you don't throw in to B, you have to throw into the complement. Alright, so let's keep that same universe, the 1 through 10, and I want you to see if you can find the complements of C and D. Alright? The complements of C, I'll write that down, C prime, that's what you're looking for. And you're also looking for the complement of D. So push pause on the video, see if you can find the complement of C prime, complement of D, and then also let me do two others. Let me do the empty set. Find the complement of the empty set, and find the complement of the universe. Alright? We know the empty set is a set containing anything. So let's find the complement of the empty set and the complement of the universe. Again, push pause and try these on your own. Alright, so to get the complement, you should have, for C, or complement of C, we have 1. Basically everything except for 1. So 2, 3, 4, 5, 6, 7, 8, 9, 10. So the set containing all of those elements is C complement. Notice that as far as D complement, we have a 1, 2. We do not have a 3, so that goes in the complement. We don't have a 3 in D, so that goes in the complement of D. We have a 4, we have a 5. We don't have a 6. 9, we don't have a 9. Everything else is represented in D. So 3, 6, 9, at least the set containing 3, 6, 9, is our complement of D. Now if you think about it, the empty set has no elements. So what we have to put in the complement is all the elements in our universe that aren't in the empty set. That turns out to be all of the elements in our universe. And then a very similar argument, if I take all of the elements in our universe and I say, what's their complement? Well, by definition, all of the elements are there, so there's no element left out. So the complement of the universe is the empty set. Okay? Now notice something, it's going to work like this always, that if I take the complement of a complement, so the complement of the D prime here, if I say what's the complement of 3, 6, 9, well, it would be the original set, 1, 2, 4, 5, 7, 8, and 10. If I said what's the complement of 2, 3, 4, 5, 6, 7, 8, 9, and 10, the complement of that would be 1. Okay? So these two sets are, in other words, complements of each other. Right? Same thing, the universe and the empty sets are the universe and the empty set, universe, empty set, are complements of one another, because the complement of the empty set is the universe, and the complement of the universe is no elements at all in your set. The next relationship or interaction that we're going to look at is the idea of intersection. Now the intersection of two sets technically is the set containing elements which are common to both. So I think of it as where the sets overlap. Which elements do the sets overlap in? Now the notation of the intersection is this A, if the intersection of A and B, you do A, and then it almost looks like a subset kind of thing turned on its head, but or a U upside down without any tails. But this is the symbol. It's basically a big arch. Okay. And the big arch represents intersection. So let's take two pretty straightforward examples. I want you to push pause and find out where these sets intersect. All right. Hopefully you see that these sets, well, the first two sets, have common elements of 2 and 4. All right. So my A and my B, I mean, obviously there's other elements in A, right? 1 is in A, 3 is in A, but 1's not in B and 3 is not in B. Same thing with 6 and 8 in B. There's no 6 in A, there's no 8 in A. So the only thing we have common to both are the elements 2 and 4. And so the overlap, where these two sets overlap, or where these two sets intersect, is 2 and 4. Now, this is the formal way of writing it. We say A intersect B is the set containing 2, 4. Now, in my next example, I gave you a little bit more of a thinking idea. And I'm doing this so that we can sort of lead up to logic if we do cover that in the next chapter. So, if A is the set of cities in Michigan, so think of A is going to include Mount Pleasant, it's going to include Detroit, it's going to include Lansing, it's going to include Traverse City. all cities in Michigan. And B is the set of cities in the United States with more than 150,000 people. So B has things in it like New York, Chicago, Los Angeles, bigger cities, right? Then what would you say is the intersection of A and B? Well, we have to, since we want things from A, all of the cities that we pick have to be in Michigan. And since we're talking about intersecting with B, what we're looking at is all the cities in Michigan which have more than 150,000 people. And by the way, in that set, if you look it up, or at least on the last census data, the two cities in Michigan are Grand Rapids and Detroit. Okay, I think all of the other cities have slightly less than 150,000. So Lansing has more than 100, but not quite to 150,000. And there's a lot of cities. There's some other cities you can think of, Saginaw, and Flint, and all those places. So, anyways, there are two cities in Michigan which have over 150,000 people, at least on the last census. All right, so let's take these sets. Now, there's two purposes for me labeling these sets. I want A to be the set containing A, B, C, and D. I want the set B containing C, D, and F. Notice that when I do this, and this is going to be very common when you talk about set theory, oftentimes the sets are given the capital letters, and the elements of the sets are given lowercase letters. Okay, and so that distinguishes. And a lot of you probably in lower algebra classes may have used capital letters and lowercase interchangeably. Well, in mathematics, it is important that you keep these things straight. So what I want you guys to do is I want you to find A intersect B, A intersect C, and B intersect C. Also, I want you just to notice that when I say B intersect C or A intersect B, these are always the same as if I'd have switched it. So if an element is in B and C, well then it's also in C and B. All right. So the order here, B and C, C and B. So if it's in both those C and B, then it's in both B and C, right? So the order does not matter which way you put this. So if you say in the first one, B intersect A, that's the same thing. So push pause and try to find the intersections of these sets. Alright, if you've done that, then you should see that the intersection of A and B, alright, well, they have a C and A, and a C and B, and a D. So the intersection is C and D. That's where those are the elements which are in both. If I look at A and C, well, A and C don't share any elements together. So the intersection, there's no elements which are in here and in here. So if there's no elements, that means that the intersection is the empty set. Okay, it's the set containing no elements. We see now why sometimes empty sets can be important. Because when we talk about two categories and we say there's no such thing, there's no overlap, or there's no intersection, the idea of empty set comes up. Now as far as B and C go, the overlap for those B and C. So we have a C, a D, and an F in B. We have an E, F, and G in C. So what we have, I think, the only letter that's common to both is an F. And I'm trying to draw this on a iPad, so my set brackets aren't quite as good as they usually are. But the common to both is F. The next type of operation that we're going to deal with is the idea of unions. All right. Now, a union kind of means, well, technically, it's the set containing all elements which are in either A or B. So it's basically I throw all of the elements in A together with all of the elements in B and make a new set. Okay, so I combine the two sets. And the notation here is A, and it almost looks like a U, but without a tail, right? So it is the intersection flipped upside down, okay? And there's reasons for that, but the idea here is that the symbol is the intersection flipped upside down. It looks like a U without a tail. So here's what I want you to do. I want you to push pause and try to find the union in these two examples of A and B. So we want to find A union B in both examples. Push pause and try to do it yourself. All right, so in the first case, again, we're trying to throw these things together. So since the number 1 is in A, it's going to be in the union. So everything that's in A is in the union, and everything that's in B is in the union. Now, one thing about this, if you look at the number 2, it occurs in both places. So it is in the union because it does occur in A and it does occur in B, but you don't have to write it twice. Since this is a set, we don't repeat entries. We don't have to repeat entries. So the union is A union of A and B is 1, 2, 3, 4, 6, and 8. All right. And of the states, by the way, the reason I chose these states were, these are the 5 biggest states by population. These are the 5 biggest states by size. All right. So if you talk about 5 biggest states by population, union the 5 biggest states by size, we will get, well, everything: California, Texas, New York, Florida, Illinois. I have to go down here. First off, switch that. Alaska, Texas. Oh, we already have Texas, so we don't have to. We shouldn't have wrote that twice, right? So erase that. California, we've already have. Montana. Oops. Montana. And New Mexico. So notice we didn't have to write California or Texas twice because they're in there once already. So all of these, this set, the union, is the set of these 8 states. All right? All right, so I want you to push pause and then try to find the following things. Remember, we're talking about unions here, so let's do A union B and A union C and C union B. And just like intersections, I hope that you understand that if you throw B and C together or A and B together, the order is interchangeable. So C union B is the same thing as B union C. So push pause on the video, and then I'll come back and do these. Alright, so A union B, if you put these two together, we're going to have A, B, C, D. We've already written C and D, so F is the only thing remaining. Alright, so you can see that what we've done again is combined the top two, the A and the B, these sets. And when you write these, you do not have to put anything that repeats twice in twice. You just put it in once. So C is in both places, but it only needs to be put in once in A union B. A union C, we're going to get A, B, C, D, E, F, and G. By the way, these were the same A, B's, and C's we had earlier. Same sets we had earlier. Okay. So A, B, C, D, E, F, G. As far as B union C goes, I'm going to write these in letter order. So that's what we get. C, D, E, F, and G. Alright. Now, we're going to look at intersection and unions through Venn diagrams. And I just want to point out, what we're going to do is we're going to assume that there's some overlap. So again, Venn diagrams, we always want to start with the rectangles. And let's start with A and B being circles. I'll put red circles here. A and B, A and B. Okay? So in one of these, I'm going to put the intersection. I'm going to show you where in Venn diagrams that appears to be. So let's put intersection. And then the other one, we're going to put a union. Alright? So as far as the intersection goes, intersection, remember, is elements that are in both A and B. So to be an element of both A and B, we obviously can't be outside of the circles. So we have to be inside. And if I'm inside right here, then I'm in B, but I'm not enclosed in A. If I'm inside the circle here, I'm in A, but not in B. So to be in both, you have to be in this region. So what I'm going to do is I'm going to shade that region, basically. So this shaded region in here is the intersection. Okay. Now as far as unions go, remember, if something is in A, then it's in the union. So if anything is in A, any spot in A, it's going to be in the union. And if anything is in B, it's going to be in the union. So if I was to shade A union B, I get essentially both circles together. Alright. Now there are some times that I'm going to ask you to shade, given a diagram, or just to draw your own diagram and shade the intersection, the union, the complements, and all of those kinds of things. Now, what comes interesting is the idea of relationships between unions and intersections. Okay? And this can be seen from Venn diagrams. Let me go back to the Venn diagram, or I'll draw this in red up here. If we have A and B, and we want to throw the union in, okay? So let's take the union. The union is all of this section, all of the A. It also includes the intersection. So let me put that in, let's say, a different color. Let's put that in. Put in light blue, intersection. And it also includes the B. The B and not. Now I want you to notice something. That A union B comprises all three of these parts. The pink, the light blue, and the purple. Now A itself is both the blue and the pink together. So if I'm trying to count the number of objects in A union B, and I just add up A and add up the number of objects in B, what I've done is I've double counted this intersection. So A union B is that region where all the shading happens. If I do A, I get pink and blue. If I did B, I'd get blue and purple. So if I was trying to find A union B, and I was trying to find the number of things in A union B, what I'd have to do is count up the number of things in A plus the number of things in B and throw away the intersection. Now let's let's take that and I'll show you that that worked in an example. Alright, so previously we had the following sets. We had A, which was lowercase a, B, C, and D. And we had B, which was C, D, and F. Oops. And we saw that A union B had A, B, C, D, and F. Now notice the union has 5 elements. So the cardinality of the union equals 5. A itself had 4 elements. B had 3 elements. So if I was looking for the size of A union B, basically what you're going to have to do is you're going to have to take the size of A plus the size of B and then throw out the size of the intersection. Now, I didn't write the intersection yet, but it has 2 elements. Okay, in fact, the intersection is CD. Let me write that. Let's see if I can do it fairly small. A intersect B equals C, D. Okay, so it should be fairly obvious that if I'm looking at this, 5 is equal to 4 plus 3 minus 2. And you should see the pattern. Here we have these 5 objects, and they came from putting 4 and 3 together, where 2 of them overlapped. So the general rule of A union B, the cardinality of A union B, is being the same as the cardinality of A plus the cardinality of B minus the cardinality of the intersection, does work in this example. And that can be said without actually knowing the sets. So for instance, if I know that the cardinality of A was 17 and that the cardinality of B was 20 and the cardinality of their intersection is 5, then you can use the formula to find the cardinality of the union. Alright, so what you would do is you'd say, okay, union is, start with A, 17 objects, throw in B, 20 objects, but we've double counted the intersection, so we have to throw out 5 objects. So the cardinality of the union is, 32. All right. So I want you to try another example. Assume we have some other A where the cardinality is 15, and we have a B such that the intersection is 6, and the union of A and B, cardinality, so the union of A and B have 38 elements. Can you find the cardinality of B? So push pause on the video and see if you can do that. All right, so basically, again, it comes down to the formula. The formula says cardinality of A union B. So I'm going to write this in green or something. Cardinality of A union B, 38, is equal to cardinality of A plus the cardinality of B, I don't know what that is yet, minus the cardinality of the intersection. So that's 6. Okay, so you can just take and solve this algebraically, right? The 38 is going to be equal to 9 plus the cardinality of B. And so the cardinality of B has to be equal to 29 in this case. All right, so the cardinality of B equals 29. And that's the final answer. So if ever you're given the size of 3 of those things, whether it be the intersection, the union, the set A, or the set B, then you can always find the 4th element. Alright, the last operation that we're going to talk about is set difference. And set difference is basically a little bit what it sounds like, although you have to be a little bit tricky. What we're doing is, when I say A minus B, right, that's what I mean by set difference, A minus B. I'm going to start with the elements in A, and I'm going to throw out any elements that are in B. Okay, so let's do a couple of examples of this. Let's look at this A and B, and remember, you always start with the first one. So you start with A in this case, and you throw out any elements of A which are also in B. In this case, you start with B and you throw out any elements that are also in A. So I want you to push pause and try to do this one. Alright, so hopefully you've done that. I'm going to start and do this for just a second. So we start with elements of A. That's 1, 2, 3, 4, 5. And the minus B, 2, 4, 6, 8, 10, is going to cause us to throw some out. And so the ones that we're going to throw out are 2 and 4 are the same. So 2's in B, 4's in B. And 6, 8, 10, none of those. So the set difference for A minus B is going to be equal to 1, 3, 5. So the set containing 1, 3, 5. If I do B minus A, start with B, 2, 4, 6, 8, 10. And we're going to throw out anything that, so we start with B, we throw out anything that's in A. Throw out the 2, throw out the 4. Okay. And so you're left with the set difference being 6, 8, and 10. So B minus A is 6, 8, 10. A minus B is 1, 3, 5. Okay. Now let's draw a diagram of what the set difference looks like. So if I have a universal set, and I have inside here some set A, and inside here some set B, okay? What I'm looking for is all of the elements of A. Let's start with A minus B, obviously. So we're going to look for A minus B. In fact, let's change the color on that. I will erase that. We are looking for A minus B, and I want to shade that. So I'm going to start with everything in A. So I start with this huge circle, and then I throw out anything that might be in B. So I'm going to throw out this circle, this section. In other words, I'm going to start with A and throw out the intersection. Okay? So what that means is, if I can draw this well, this is going to be, this shaded region is going to be A minus B. And on a similar argument, if you did B minus A, okay, this is A, this is B, the shaded region of B minus A would be the part of the circle that's in B but not in A. Alright? Now I will say something. As far as intersections and things of that nature go, this can be written in a variety of ways. Okay? So we can write this as of A's and B's with complements and unions, or complements and intersections. I'm not going to get into that right now, but we might see that in the next section.